Okay, so what we're going to do here in this video is, again, continue on with E2 reactions. So specifically, in this particular video, we're going to discuss E2 reaction with respect to the substrate in the reaction, which realize is the alkyl halide. Okay, that's the substrate in our E2 reactions. And then in the second half, we are going to actually talk about alkenes, their stabilities and things like that. Briefly discuss nomenclature because it's very similar to the nomenclature of alkenes. It's just very slightly different from that. Okay, so we'll get into that in a bit. Okay, so again, to give you an overview, again, E2 reaction is where we have some alkyl halide which reacts with a base, and I'm going to pick maybe sodium hydroxide as the base here. Okay, so there's an alkyl halide that's reacting with a base, and what we get out of this reaction is an alkene. So this is the alpha carbon, this is the beta carbon, plus we're going to get water, and we'll have sodium bromide in this case, and then realize that our solvent in this particular case is usually the conjugate acid of the base, so water is fine, and E2 reactions are made favorable with heat. Okay, so if that's the reaction, then we are going to focus on our substrate. What do we know about the substrate? So it turns out in E2 reaction, the relative rate of reaction with respect to the substrate, okay? That means which substrate reacts the fastest, okay? So the relative rate here with respect to the substrate goes in this order: tertiary alkyl halides. Okay, we are always going to talk about alkyl halides. So tertiary alkyl halides, these react the best, okay? These react the fastest. So tertiary alkyl halide, which are better than secondary alkyl halides, and then primary alkyl halides do not, or which are greater than primary alkyl halides. And then we have methyl, these do not react. Okay, so it's kind of opposite to what we saw in an SN2 reaction. In fact, the same is true for primary. Okay, so primaries do not react, but there are exceptions. Okay, these don't react usually in an E2 reaction, but exceptions are there to this situation. Okay, but tertiary alkyl halides, they react the fastest, then secondary. So it is pretty much a reaction of tertiary alkyl halides and secondary alkyl halides, except for some scenario, primary would not react. Okay, and then methyls just do not react because methyls do not have a beta hydrogen, so they cannot do an elimination. So methyls only do substitution SN2 reactions. In fact, only SN2 reactions. Okay, so that's the order. So why is this the order? Okay, that's the obvious question that should come to our mind. Okay, so if we look at, let's say, a tertiary versus a secondary or a primary, let's say, okay, so if we draw out, let's say, a tertiary alkyl halide, and let's say that's a tertiary alkyl halide we used in our video earlier. This alkyl halide will react with hydroxide, which is our base. I'm leaving out the sodium part here. and let's say the hydroxide also reacts with a primary alkyl halide. Okay. And the tertiary alkyl halide under these conditions with water, heat, and water would give us an alkene. The primary alkyl halide, this is alpha, this is beta. Either one of those, I could put the double bond anywhere. Actually, I want you to, maybe I should put the double bond at a different position this time. That's beta. And I'm going to put the double bond here. So that doesn't change anything, it's the same alkene. And then when we have the primary alkyl halide, this is alpha and this is beta. So that means our product should be like this. And plus, we are going to have water, and we are going to have bromide, and we are going to have water, plus we are going to have bromide. Okay, so if we compare these two reactions, which are sort of like the extremes for any two reaction, we're looking at the at an example of a substrate which reacts the fastest, or these are the most reactive in some sense. Okay, these are the most reactive, and that's the least reactive. Okay, so we're looking at the substrate that's the most reactive in an E2 reaction. We're looking at a substrate that's the least reactive in an E2 reaction. So overall, everything else is constant for both substrates. So if one of them reacts better or is more reactive than the other, there are only two things that are different in the scheme. The alkyl halide itself is different. Okay, one is a tertiary alkyl halide. This is a tertiary alkyl halide. This is a primary alkyl halide. And then the alkene is different. So it has to be one of these two, either the alkyl halide or the alkene itself, which determines why tertiary alkyl halides react are more reactive in an E2 reaction. Now, as far as the alkyl halide is concerned, realize that the base comes and gets this beta hydrogen. This is a beta hydrogen. That's the hydrogen that the base deprotonates. Okay, and then those electrons fall here, the bromine goes away. This is going to go deprotonate that beta hydrogen. Those electrons fall here, and then the bromine goes away. That's the mechanism of the reaction. So as far as the base is concerned, whether it's getting this beta hydrogen from a primary alkyl halide or from this tertiary alkyl halide, it shouldn't be that different, because unlike SN2, where the base has to approach that alpha carbon, and so sterics play a role, that's not the case in an E2 reaction, because it's not trying to approach that alpha carbon. All it has to do is just grab a beta hydrogen that's like outside. So it can just basically go grab that beta hydrogen. Now, we'll see later that there are other things that we can control in this reaction. But for now, it looks like whether it's grabbing this beta hydrogen or that beta hydrogen, it shouldn't be that big of a difference. Okay, so that means the alkyl halide itself, there would be like some difference, but it doesn't seem to offer like a very huge difference in terms of why this is more reactive compared to the primary alkyl halide, why the tertiary is more reactive compared to the tertiary, why the tertiary is more reactive compared to the primary alkyl halide. So that means that the outcome, okay, whether the reaction goes well or not, is actually controlled by the alkene itself. Okay, so the alkene, the stability of the alkene determines relative reactivity in E2. Okay, so the stability of the alkene determines the relative reactivity in E2. Okay, for lack of space, I'm going to write it here. A more stable alkene product results in a faster reaction. Okay, so the more stable the alkene product is, the reaction itself goes faster, or the alkyl halide is going to react faster. And so what that means is, between the tertiary and the primary, the alkene that's formed here is more stable than the alkene that's formed here. Now, we've already discussed alkenes a little bit when we did E and Z configurations. So hopefully you still recollect that I can differentiate these two alkenes by the substitution on these double bonds. For this alkene here, there is no substituent. There are no substituents on both carbon atoms. So this is basically like an unsubstituted alkene. Whereas for this tertiary alkyl halide, or for this alkene, we can call it a disubstituted alkene, because when we look at the double bond, it has two substituents to it. What those substituents are doesn't matter. Basically disubstituted alkene. So we'll look at this in a little bit more detail, okay? What factors control the stability of alkenes? Because that is what determines which product is formed, okay? So stability of alkenes. So one thing is, more substituted alkene is more stable. Okay, so if I were to draw out a few alkenes, okay, let's say if we look at these alkenes, we can kind of qualify them based on the substitution. And again, for doing the substitutions, what we're doing is we're basically looking at the two carbons that are double bonded to each other. That's our double bond. And essentially, you're looking at the number of substituents on these carbon atoms. So when I look at this double bonded carbon atoms, you can see there is one substituent, there is a second substituent, there's a third substituent, and a fourth substituent. So there are 4 substituents on this double bond. So we'll call this a tetra substituted alkene. Okay, this is a tetra substituted alkene. For this alkene, about the double bond, we have 1, 2, and 3 substituents. So we're going to call this a tri substituted alkene. So tri substituted. Similarly, these two, okay, these are di-substituted, and then we have a mono-substituted. So mono means 1. Okay, so there's only one substituent on the alkene. So you can basically classify alkenes as tetra, tri, di, or mono substituted. And since a more substituted alkene is more stable, what that means is tetrasubstituted alkenes, these are more stable than tri-substituted alkenes, which are more stable than di-substituted alkenes, and these are more stable than monosubstituted alkenes, which in turn would be more stable than an unsubstituted alkene. If there is no substituent, like we had in the previous basically in the board work, that is an unsubstituted alkene, that would be like the least stable of these two. Okay, now between di, tri, and tetrasubstituted alkenes, okay, so these are both di-substituted alkenes, so that's one thing. Now the reason why this happens is, okay, I think I should do that before we go away from this board. Okay, the reason why this happens is because of this effect called hyperconjugation, which we discussed when we were discussing carbon-based intermediates. So please go back to the video on carbon-based intermediates, look through the portion on radicals and carbocations, more substituted carbocation, or why a more substituted radical is more stable. It is the same reasoning here. Okay? So essentially, for let's say a tetrasubstituted alkene, if I were to draw this slightly differently, that alkene, let's say this is our carbon. These are the two carbons which are double bonded to each other. And then there are 4 substituents on them. So let's assume there's one substituent here. The S substituents going there. And realize that these carbons are sp2 hybridized, both of them. Okay, so going back to chapter 1, and this is why I said in organic chemistry we basically will be referring back to like all of our previous chapters as we move forward. Okay, so going back to chapter 1, hybridization tells us about the shape or the geometry around that atom. So since these carbons are sp2 hybridized, these are trigonal planar, so they're flat. That's why I'm drawing them flat like this. And in fact, that is how we've seen an alkene in chapter 1. And essentially what they have is each sp2 hybridized carbon should have a p orbital on it that's perpendicular, orthogonal to this trigonal plane. And so both of these have p orbitals here. Okay, and these are carbons based on this structure. These are all carbons which have hydrogens on them, but these are sp3 hybridized now. Okay, so they all have, they're methyl groups essentially. So this is what we're looking at overall. And then the two sp2 hybridized carbons, realize they have p orbitals on them, which are orthogonal to this plane. And this double bond or the pi bond, that's basically an overlap of these two p orbitals. Okay, these overlap with each other to give us the pi bond. That's how the pi bond is formed. So when you have a tetrasubstituted alkene, okay, the sigma bonds here between these carbons and the hydrogen. So in some sense, if we call these carbons alpha, because that's a functional group in some sense, so those are the alpha. No, let's say if we, that won't be right. So let's say if we call these alpha, okay, no, I don't want to use the alpha term actually. So essentially what we're saying, the carbon 1 here, 2, then the second carbon has a hydrogen bond here, a carbon-hydrogen sigma bond, which has electron density in it. In fact, all of these bonds, they're going to line up with this pi bond. And so what they can do is they can share electron density with this pi bond. So go back to that video on carbon-based intermediates where we discussed carbocation intermediates, but this sort of a bond or electron sharing between the sigma bond of the carbon hydrogen, from the sigma electron density on the carbon hydrogen bond with this pi bond essentially, okay? And some of these might be able to share with the bottom lobe like that. Okay, so there's basically an electron sharing, density sharing between these orbitals, and that stabilizes the alkene itself. So you can see as you go from a tetra to a tri to a di to a mono, you're basically cutting down on the number of groups that are able to do this sort of a sharing. And therefore the alkene becomes less stable. Okay, so a more substituted alkene is more stable, and this effect is called hyperconjugation. So we went over that in the carbon-based intermediates portion. Now, another very simple way, like a very crude way to discuss the stability is to think about it like these carbons are sp2 hybridized. These carbons are sp3 hybridized. And what we know again from chapter 1 is that sp2 hybridized carbons are more electronegative than sp3 hybridized carbons. So in some sense, there's also going to be an inductive effect. So because these carbons are more electronegative, they're going to pull away electron density from the neighboring carbons. And if there are more carbons to supply electron density, then that would make these sp2 carbons feel a little bit more stable. And I think that's a very hand-wavy, like crude way of discussing this. The hyperconjugation effect explains why a more substituted alkene is more stable. Okay, so because of that, essentially a more substituted alkene is more stable. So that's one thing. Now, for di, tri, and tetra substituted alkenes, that's one thing that determines stability of alkenes. The second thing is, remember, trans alkene is more stable than cis. Okay, a trans alkene is more stable than cis. Or if we generalize this, E alkenes are more stable than Z alkenes. Okay, so that's another trend. So when we were looking at di-substituted alkenes, when we have a trans, now in this particular case, this is also E compared to cis or Z, the trans alkene, this is more stable compared to the Z alkene. Okay, so that's another effect that we need to keep in mind. So trans would be more stable than the cis alkenes. And so these are two things that would control the stability of alkenes. And so they pretty much help us understand why a tertiary alkyl halide is more reactive in an E2 reaction, because a tertiary alkyl halide is going to give us a more substituted alkene. Okay, and then this has other effects, okay, or other repercussions in some sense. So let's look at this example here. let's consider an example where we have an alkyl halide here. This is an alkyl halide. And let's say we react this alkyl halide with NaOET. Again, I'm just choosing a strong base and polar protic solvent with heat. Okay, we're doing an E2 reaction. So whenever you see an alkyl halide, you see a strong base, which is also a strong nucleophile, but then you see a polar protic solvent, and then you see heat along with that. That should hint towards an E2 reaction. Now, sometimes heat may not be shown, so pay attention to the polar protic solvent. And then towards the end, we will sum everything up and we'll see what are other things that would help us identify whether it is SN2 or E2. Okay, so we do this reaction here. So for this particular case, this is our alpha carbon, and now we have beta here, and we have beta on this side. So we have beta carbon on the left side, we have beta carbon on the right side. Notice how they are not identical, because this beta carbon is a methyl group, this beta carbon is a CH2, which is again connected to more carbon. So they're not identical. So we're going to differentiate the two. We're going to call this beta prime. So this is a beta prime, this is a beta carbon. Okay, now they have hydrogens, okay? So we have we have H beta here. And again, there are two hydrogens. I'm only drawing out one because only one of those beta hydrogens would involve in the E2 reaction. We call that H beta. I'm going to call this H beta prime. And again, there are three beta hydrogens on the beta prime carbon, but I'm only drawing out one because we only need one. So now the base here, when it reacts with this alkyl halide, it has two options. It could go and react with the beta hydrogen. Okay, it could go react with the beta hydrogen. And in this particular case, the bond between H beta and C beta would fall into the space between alpha and beta, and then the bromine would get kicked out. To keep it consistent, let's do that. The bromine gets kicked out. This would give me a product, 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons. This is alpha, this is beta. So this would give me a product where there's a double bond between the alpha and the beta carbon. Now we've drawn only one product that's possible when the double bond forms between alpha and beta, because this is a trans product. We could as well get a cis product. This is alpha, this is beta. So, and these are both coming from the loss of the beta hydrogen, okay? This is from H beta. This is also from H beta. They're both coming from H beta. The other possibility is, because there's nothing that is basically going to stop the base from going for the H beta prime. So the other possibility is that the base goes for H beta prime. And in this particular case, the electrons between H beta prime and carbon beta prime are going to fall in the space between alpha and beta prime carbon. And then the bromine is going to get kicked out. So two possibilities. And this should give me another product now, where we have 1, 2, 3, 4, 5. The double bond is between alpha and beta prime carbons. Now, in this particular case, I cannot draw trans-cis or EZ, whichever way you call it. I cannot really do that. So that means when I have a substrate like this, an alkyl halide like this, there are 3 products that we can expect from this reaction. And we should be able to tell which one is the major product here. So if you look at this structure at the bottom, this is monosubstituted, disubstituted, disubstituted. The more stable alkene is the major product. That means our major product is not this one, okay? Or this is not one of, so the major product is one of these 2. Now, between these 2, we have trans and cis, and we know trans is more stable than cis. So that means our actual major product in this reaction is that, which is the trans disubstituted alkene. Okay, so that is something to keep in mind as you do problems. Always look for examples. You know, so let me see if there's an example that I can get easily to show you guys this thing here. Okay, I think what I'll do is I will select some and then I will try to do some together, but this is something to keep in mind. You have to think about all possible beta prime, maybe beta double prime. That is a possibility. Okay, let me just quickly do an example like that, where there are 3 possibilities, let's say. Okay, so let's say we have an example. We have an alkyl halide where we got let's say let's say this is let's say that's our alkyl halide. So now this is a tertiary alkyl halide, and we're going to react this with sodium hydroxide in water with heat. Now, usually when I will make quizzes and exams, and I want you to think about E2, I would include all 3 of these parameters. Okay, I will include a strong base, I will include a polar protic solvent, and I will include the heat. Unless it is one of those cases where it's very obvious, where the other reaction just cannot happen, let's say. So for example, in this particular case, even if I did not include water and heat, and all I give you is this alkyl halide and sodium hydroxide. So you have an alkyl halide and a sodium hydroxide. Is there a way for us to tell whether this is an E2 reaction or SN2 reaction? We've only learned 2 reactions so far, SN2 and E2. Is there something that tells us that it's going to be one of the 2? Because realize the sodium hydroxide, this is a strong base. It's also a strong nucleophile. And we don't have a solvent shown, we don't have heat shown, nothing else. All we have is the 2 of these. So the alkyl halide, that gives it away, because this is a tertiary alkyl halide. And remember, tertiary alkyl halides do not participate in SN2 reactions. The only reactions they can do is an E2. In fact, they are the best at doing E2, because E2, they are the most reactive in E2 reactions. So those kind of things. So as you go through this material, you have to basically identify these things and be able to do it. So in a situation like this, even if I don't show you the water and the heat, you should know that this is an E2 reaction, because there's no SN2 possible. Okay. So in this particular case, this is our alpha carbon. And now notice we have beta, we have beta prime, and we have beta double prime. So we have 3 different beta hydrogens. We have H beta, we have H beta double prime, and we have H beta prime. So 3 possibilities for eliminations. Okay, and so the base now, it doesn't know to differentiate between these, so it's going to go for all of them. The product, the stability of the product would determine which one is the major product, which one's more favorable. Okay, so what we're going to do is we're going to basically do all of this. So it can go for beta prime. Electrons from here would drop, and the Br would get kicked out. And that would give me a product like this. Okay, this is one product. Now, in fact, there is another product possible here, because this is the E alkene, and you might want to work through this and convince yourselves that this is the E alkene. Okay, so we can actually write down a Z alkene. So this is Z, and these are both coming from the beta prime. Now, the base can go for beta, H beta instead, and then this electron density is going to fall into the space between alpha and beta, and the bromine will get kicked out. And in this particular case, so the double bond forms between alpha and beta now. That will be the product that we get from this reaction. Now, between these two products, I want to point something out. Notice how in the starting material, this methyl group is on a dash, the bromine is on a wedge. That's because this carbon is sp3 hybridized, so it's tetrahedral. When I go to the product, this is alpha, this is beta, alpha, beta. We have alpha, and we have, sorry, not beta, beta prime, we have alpha and beta. Notice how the methyl group on alpha now is basically a straight line. Why am I drawing it like that? Because this carbon is now sp2 hybridized. It's trigonal planar. So the geometry around that carbon needs to change, and that has to be shown in your picture. So this is, when I draw it like this, it is basically saying that, okay, I understand the geometry has changed. It is sp2 hybridized, so things are different now. Okay, so that's the product from the alpha. Now, there's another possibility here, because the base could basically go and get H beta double prime, and then that electron density would fall into the space between alpha and beta, and again that would kick out our bromine. In all cases, that is going to happen, and that would, and I did not write E or Z products for this. There is a reason for that, so you might want to work through that and understand why that is the case. Okay, and when the H beta prime is lost, I'm going to get, so this is plus 1, 2, 3 products plus another product, which is going to be this. So these are all products, and there's no E or Z for this product also. So I'm not going to include that. So think about why, okay? It's always good to go back and refresh your memories on that, okay? The concepts, go back, revisit those concepts. So we have 4 possible products here. Which one of these is going to be the major product? So if I look at these, the first alkene is a tri-substituted alkene. Second one is also a tri-substituted alkene. Between these, one is E and the other one is Z. So between these, I can say, okay, the E is major, the Z is minor, but they may not be the major products overall because they are tri-substituted. the third alkene product here, this is a tetra-substituted alkene. The last alkene product is di-substituted, so that means overall, this is our major product because that is a tetra-substituted alkene. That's the most stable alkene of all of them. Okay, so that is the major product in our reaction. Okay, so that's another example. So what we're going to do is we're going to stop this. Actually, no, I mentioned nomenclature, but let's just quickly go over nomenclature here. And maybe these examples can be used for nomenclature, one or two of those, so we can use some of these for doing the nomenclature. Let me pick some. I think it doesn't matter. We can go for one of these two. So go for that. And then we can probably do that one, and we can probably do this one also. Okay, so we'll try to name all three of these alkenes. Now, as far as the nomenclature is concerned, like I said, it is very similar to alkanes. You're doing pretty much the same thing. You're looking for the longest carbon chain. The only difference here is, okay, the only difference here with alkene, well, nomenclature is that find a parent chain which contains the double bond. So that's one requirement. So you might have a molecule where you have a 6 carbon long chain, but it does not have the double bond in it. Like the alkene bond does not show up within any of those 6 carbons. And you have another carbon chain which is only 4 carbons long, but that contains the double bond. That's the chain that we're going to go with. And we'll see one of those examples here actually. And then, so you're going to find the parent chain, the double bond. And then the second requirement is the double bond gets the lowest number possible. So when you're basically numbering your carbon chain, try to give the double bond, the carbons that are in the double bond, the lowest numbering possible. Okay, and we'll see that. So let's say for this first molecule here, if you look at it, there's 1, 2, 3, 4, so 4 carbons like this, but notice how that chain does not include the double bond. The double bond is not part of that chain, so it's not, will not go for that chain. So 1, 2, 3, 4, and it could be 5 or 5, doesn't matter, either one. It is a 5 carbon chain. Okay, so 1, 2, 3, 4, 5, or 4, 5 over there. Now, when we are numbering this, we can go from the left to the right or go from the right to the left. But if I go from the right to, so if I go from left to right, then 1, 2. Double bond shows up on carbon number 2. So 1, 2, 3, 4. I'm going to go with this carbon at the top, 5, like that. Now, if I went from the left, or sorry, from the right to the left, it will be 1, 2, 3. So the double bond is going to show up at number 3. So which is a higher number, so that we're going to keep the numbering from the left. That gives us a lower number for the double bond. Okay. Now, if we look at the substituents, we have 3-methyl, and there is a 4-methyl. Okay, so that means this molecule is a 3,4 dimethyl, okay, 3,4-dimethyl, and overall it is a pentene 5-carbon alkene. So pentene, so we're going to write this as 3,4-dimethyl pent. There's no need for a hyphen there, dimethyl pent, and the number of the double bond 2-ene. Okay, it's going to show up there to say that the double bond is on carbon number 2. Now, there is another way of writing this, which is basically 3,4-dimethyl, and then you write 2-pentene. So again, when you see this number before your parent chain's name, it is referring to that double bond, position of the double bond. So 2-pentene. Either one of these two, I would say, is acceptable. It stands, although one of them is like a newer version and then it's another IUPAC nomenclature version, but either one is fine, I would say. Okay, so that's the name of this molecule. So it is a 3,4-dimethyl pent 2-ene. So now let's go ahead and name this molecule here. So again, we have the double bond here, so we must include that. And so I think looking at this molecule looks like 1, 2, 3, 4, 5. That's probably the longest carbon chain, which actually includes the double bond. Now I could have started 1 here. That is a possibility. Either way, it would have been fine. Oh, sorry. I forgot to mention something with this top molecule. Now in this top molecule, this is also an E-alkene. Sorry. It's an E-alkene. So that needs to be included into the nomenclature. So we're going to call this pent 2-E-ene. So that says that this alkene is the E configuration, okay? So that would also be included in the name, 2-E-pentene, okay, 2-E-pentene. So that must be included in the name because that's like RNS, like configuration. So that's the configuration for the alkenes. So you come down to this molecule. Now again here, I will not count from left to right because that will put 1, 2, and 3 for the double bond. I want the double bond to get the lowest number. So when I go from right to left, the double bond is at carbon number 2. So we are only looking at the first carbon where the double bond starts. That's the numbering that we give. Okay. So again, for this is dimethyl on 2 and 3. So the name for this molecule is going to be 2,3-dimethyl pent 2-ene. It's a 2,3-dimethyl pent 2-ene. Okay, there's no E or Z for this molecule, so we don't have to include that. Or you could write it as 2-pentene. Realize that you can use those. Okay, go to the third molecule here. Now this is where, if you notice, you have 1, 2, 3, 4, 5 carbons in the chain, but that carbon chain does not include the double bond. Both carbons in the double bond must be part of the chain. So in this particular case, I think the numbering that we're going to use is 1, 2, 3, and 4. Now, you might think, why didn't I go 1, 2, 3, and 4 here? Because that is also 4 carbons. But if I did that, I will get 1 substituent. But by going in that direction, whether I went 3, 4 or 3, 4 down, I've got 2 substituents now. So I've basically maximized on the number of substituents. So this molecule here, it has 2 substituents. There is a 2-ethyl, so ethyl on second carbon, and there is a 3-methyl, and there's no E or Z for that molecule again. So this molecule is going to be 2-ethyl, 3-methyl, 4 carbons, so but 1-ene. That's the name of the molecule. Now, if there is a halogen somewhere, like a chlorine or something, if let's say that's the case, you will basically include that. If there's another chiral center somewhere, you will include RNS for that. So all of those things, they're still similar to how we did alkanes or alkyl halides earlier, okay? So I think that is basically E2 reaction. Again, we just focused on the substrate. We talked about how the substrate affects the reaction, okay? More videos to come on the E2 reaction itself.